All right. Thanks, Peter. Um, Hopefully everyone can hear me okay. So today I'm going to be talking about this paper, uh, KTO, which is Kahneman-Tversky optimization. So it's looking at how we can align large language models, or just language models generally, using theory from using methods from prospect theory, which was created and popularized by Daniel Kahneman and Amos Tversky. Um, so Peter actually suggested this paper, so thanks, Peter. It's actually really interesting, so I'm excited to get into it. So without further ado, um, basically what this paper explores is the area of like language model alignment. So we've seen last year like quite a lot of work going into this, particularly because the purpose, why do we want to align models in the first place? I guess is because we know how to create language models that learn over and train over these really large data sets like Common Crawl. But those language models by themselves offer some utility, but like we can improve their utility by aligning them based on human feedback, right? So that's where what's become, I guess, the state of the art here is aligning language models using reinforcement learning, so RLHF, and a really popular one now is DPO, which stands for direct preference optimization, which is mathematically equivalent to RLHF, but preferred usually because you don't have to do the whole like reinforcement learning part of it. I think it frames it as a supervised learning problem. Damien presented the paper, I believe, some time ago, so you can check it out on YouTube. But this paper explores yet another way of aligning large language models. But before that, it starts by understanding that it starts by making some claims about how, like, perhaps the success of these alignment methods relates to how they learn and incorporate human biases. So it introduces this concept of like a human aware loss function. So this is like a loss function that is directly related to like human preferences. And so therefore learns to incorporate some like human biases in the alignment process. So what they're doing here is they're proposing a new human aware loss function, which they call KTO after Kahneman and Tversky. And it's quite neat, it's quite simple, and they show that it can match or even exceed the performance of direct preference optimization for models. They explore models from the 1 billion to 30 billion parameter range. So we're going to go into that and what the method is and the experiments that they've run. So I think some interesting background that I wanted to point to, or why this is interesting, is one of the big things that they introduce as context is the fact that like preference data is harder to come by data. It's like expensive to collect, right? So in order to have preference data, you need to have an input X, you need to have two outputs to compare, and so you need a human to say this output is better than this output. So this can be expensive to collect in the real world, and one of the most like sort of beneficial things about their method is that it removes the need for this kind of preference data, instead opting for a much simpler, like this example is like desirable and this example is undesirable, which is data that the kind of feedback that is much easier to collect in the wild let's say, versus preference data, which requires a lot more thought and like in terms of how you collect it. Yes, that's like a little bit of context. So they kind of like introduce why, like what are some of the benefits of KTO as well, apart from that. So, well, they show that it matches like DPO performance at different scales. Interestingly, also another benefit is that it can handle not just not needing preference data, but having much more imbalanced data sets. So whereas in preference data, you have pairs of good and bad, you could have like 90% of your data set in this case be good examples and 10% be bad examples, or vice versa. And we can still match the performance of alignment using DPO, which is quite crazy. So we'll go into the experiment. And another thing that they discover, which is also fascinating, is that you can actually, so DPO and RLHF are usually give examples on the data collected. Yeah, sure. I'll go into that in the like experimental setup. So for DPO and RLHF, usually you have to go through these process. So you do your initial language model training. Then usually you'll do supervised fine tuning. This usually is of the form of like instruction tuning. So you turn a language model and you tune it to learn to respond to like instructions. So you have like input output pairs and you fine tune the model based on those input output pairs. And then you apply alignment on top of the supervised fine tune model. So you would apply RLHF or DPO to get a instruction fine tune model that's more aligned to human preferences, and therefore we consider it to be a higher utility model. But what's fascinating is that with KTO, you can actually bypass the supervised fine tuning, like the instruction tuning, and still get equivalent performance based on some of the metrics they use, which is super valuable because you can skip a step. But it's kind of interesting that it can kind of learn more end to end and not require these two like different steps. Cool. So that's a bit of a teaser of like what we're going to get into. As Peter said, if you have any questions, feel free to write in the chat or jump in and mute yourself. Cool. So as I mentioned, we have these different stages to get into the models that we use, like ChatGPT and Anthropic and all these models. You'll have like the pre-training using these like really large data sets. You'll have the supervised fine-tuning, which is where you have input-output pairs that you fine-tune the model on to get it to be in most cases it's this instruction fine-tuning, so you get the model to like learn to output responses to an instruction rather than just keep generating text. And then you have the alignment. So RLHF is reinforcement learning from human feedback. Won't go into that too much, but you basically have like your preference pairs. So given an input, you have two outputs, one with a higher preference than the other. And you want to maximize the probability of generating, or the likelihood of generating, the preferred output, but with a penalty to like make sure that the supervised fine tune and the new models don't drift too much. And the purpose of that is that you don't want to lose some properties of the model, like it being able to generate grammatically correct text or things like that. So you want to sort of get the model to be aligned without drifting too much from what the reference model is. And they don't really go into DPO in the background, but DPO is like RLHF, but it's like a closed form loss, and you can sort of train. It uses the language model itself as a reward model, and so you can it leads to like a smoother training and alignment process. So where does prospect theory come into all this? Like, how have they brought this like this field of study from years ago into machine learning and into this problem of alignment? So prospect theory was derived by Kahneman and Tversky in the 90s. And it's a theory that they were studying basically human behavior. Before that, the predominant school of thought was that human behavior was rational, and we would take decisions that maximize expected utility. And the breakthrough here was that actually that's not true. Humans tend to have certain biases, but those biases are like well defined. So one of the like key examples is loss aversion. So in the study, so they give an example here, somewhere else. They give an example that if I offered you the chance to win $100 with 80% probability, or come out with a zero with 20% probability, people might accept, like a lot of people would accept $60, even though that's lower than the expected value, but just because people have like loss aversion. So people would rather bank on the certainty of $60 than take a bet to try to maximize the expected utility. So that's called loss aversion. And another way to think about it is like, if we tend to place greater weight in our mind to like take a gamble that would lose us money than gain us money. And that's captured by like a value function. So that value function maps some kind of outcome to our like perceived value of that outcome. Then there's a couple of other parts that are important in prospect theory, like a weighting function, which captures the fact that we tend to overestimate the chance of rare events and underestimate the chance of like common events. So we have like a sort of distorted view of probabilities, but that's not so important for this paper. I think the value function is the most important part. And so in more formal terms, like the value function, you can think of it as like you have a reference point. And the reference point in prospect theory is important because like the perceived value is different based on your reference point, based on your like monetary status and whatever.
One quick question, if I may.
Yeah.
So this this variable that is being valued, valued by a value function, it surely must depend on what variable that is, right? If is it like money? Is it the amount of food you get, or something? How do you put this into like one theory that sort of generalizes?
Yeah, it's a good point. I think like a lot of times I think they explored it mainly with like monetary things. That's kind of how I've interpreted it, at least, is like it's some kind of monetary outcome.
Because that then begs the question: how can you apply it to anything that is not the monetary value, right?
As in, does it apply to things like? Because you could generalize it, right?
Exactly. I mean, isn't that what we're sort of trying to do here? That we say we have this value functions, which I assume are measured experimentally, right? So I think they use experiments to find these, but yeah, it's I don't know. It's putting it as a theory is maybe quite a lot, no?
I have a theory about this theory. That it works well. It might work well for natural language because of the fact that like this idea that we worry more about losses than gains, for example, or something along those lines. That kind of makes sense to me from the perspective that like an incorrect answer, like maybe not, how do I put it? Like you have to get the language right in an answer for it to make sense and for it to be good. But like maybe we don't care as much about it being super good. You know, so we don't have this like, if the answer is twice as good as like a baseline answer, we don't really care that much about that, but we do care if it's twice as worse, because if it's twice as worse, because we're using language and it's such a specific way of it has such specific syntax and meaning that getting things wrong can be worse. Something along those lines is what I
So
was
we're happy about a generic answer rather than a good one that occasionally is like obviously bad.
Yeah, something like that. I don't know. That was because I had a similar thought, Arvid, when I was reading this paper.
That's a good point. I think it's more like almost like a coincidental similarity rather than there's like a deep connection between the two, perhaps.
Yeah, I think so. It's kind of like, I do think the prospect theory is like an inspiration rather than like a deep connection, because I think if the inspiration comes from weighting, adding as I understand it, it's just like adding a parameter that weights desirable outcomes versus undesirable outcomes differently.
Yeah.
Cool, thank you.
Avoiding price of failure is too high, so mathematically we can define it like when we fail, it's fairly negative bias.
Yeah. Interestingly, though, we'll get to this, but empirically they get to the result that weighting desirable outcomes more is preferable, or gets to better performance, which is as opposed to like we have loss aversion. They show that the model training, it prefers like prefers like gains rather than losses, or they're weighted higher. Cool. So I guess to sum it up, you basically have like the loss and the gain is sort of, you can think of as like different slopes, and then obviously they're like, they sort of tail off because your like perceived value of an outcome becomes like sort of decreases as like it increases or decreases, or the marginal difference decreases. Cool. So that was primary prospect theory, not that I've ever studied it before. And so yeah, then they go into human-aware loss functions. So I'm kind of, so one, like, as I've read this paper, I was reading this paper a few times. I don't know if it's like, I guess the point of like them going into defining human-aware loss functions is they want to show that like, do human-aware loss functions benefit in terms of like aligning these models to better outcomes? But I couldn't help but think that like, is it marking its own homework? Because like, if we're aligning these models to like our own preference, are we then obviously going to be preferring the ones that are aligned to our own preferences versus aligned differently? I'm not sure if anyone has like thoughts on this. Maybe before I get to that, I'll go into like what a human-aware loss function is. But it's a loss function that incorporates. It has like a reward function that where the reward of one output is higher than the other when a human prefers that one. So the higher like rewards higher preference leads to higher rewards, and it has some other like properties in terms of like defining the like utility of like the input output pairs. So I guess, yeah, they go into like, why does it matter if like, does it matter if we model like human biases? So they compare a couple of different methods, some which are like non-halos. So this is an example where they have like during alignment, they append like a token. Sorry, during training, they append a token to the output. And then they, during like inference, they'll add the token like good to create like good generations. I'm not sure entirely the details of this, like what the control token is and how exactly that works, but I suppose they like prompt the model to like generate good outcomes. But it doesn't learn from preference data, so it's not a human aware loss function. And they have like a calibration loss, which I guess that this one also confused me. I don't know if anyone was confused as well, but they say that this like slick loss function is a function of this calibration loss and like some regularization. And they're saying it's not halo, even though the calibration loss is human aware. Apparently, like the slick isn't human aware, maybe because it doesn't meet some of the like definitions or like other properties that they define as being a human aware loss function. But it wasn't immediately obvious to me like why this isn't a human aware loss function if it learns from preference data.
Maybe because it's zero above the value of the loss is zero above zero. So there's no like weighting put on good examples for the calibration part, at least.
Oh, I see. So maybe it doesn't map to some of these other, like some of these other properties.
I just looked at it now because I didn't see that in depth. So I'm not sure, but
yeah,
that's the only thing I could think of.
Yeah. Cool. So they have like the first two, which are not human aware, and then the third and fourth, which is DPO and RLHF, which are human aware, learn from preferences. And they compare these alignment methods across like different sets of models. How they evaluate this, how they evaluate the alignment performance is basically they, given an input, they'll get the align model to generate an output. There'll be a reference output from the supervised fine-tuning data set, and they ask GPT-4 to say which one's better than the other. So they use GPT-4 to evaluate the outputs from the align model versus the target from the data set. So the reason they're almost all like negative in this case is because they tend to lose like most of the time, not most of the time, but like a certain amount of time versus the target. But the point is that with the with these alignment methods, you get sort of closer to the target, so showing that they are like learning something and they are like winning more versus the ground truth target. Interestingly, like it seems that in the Pythia models, like the smaller models, there doesn't seem to be like a significant difference comparing non-Halo to the Halo aligned models. It seems to be that becomes more accentuated in larger models, perhaps because larger models can capture the biases better than the smaller models can. I'm not sure, but basically, yeah, like they say here, like in smaller scales, alignment doesn't seem to provide any gains. They just seem to appear in the larger models.
Well, you need like hundreds. So for big, like for this one, also interventions.
And they also show in small models that they're like they do a variation of RLHF to try to make it simpler. So they, rather than having as I understand it, rather than having a reward model, they assign +1, -1 rewards to the preference pairs, and they do like offline reinforcement learning. So they're not actually like evaluating the reward and learning. They already have a data set that they're using to improve the model or to align the model.
Reporting. Why are we
and that's like, so this I wonder how they got to this paper, but like it seems to be like this finding of using like a really simple binary reward signal in PPO led the way to them thinking like, can we reach these like PPO level performances with just a binary signal of like good, bad? And then this is the sort of foundation of KTO, which is that alignment method that they introduced. So they kind of go into like the derivation of their the loss function. So like I'll break down what I think are like the most important parts of the loss function. So you have like a KTO, like a reward function, which compares the reference model to the like new model, and that's sort of like a utility. So you're trying to maximize the log likelihood of this like input output pair. But it depends on if the outcome is desirable or non-desirable, and this is where like the prospect theory comes in. So they have these parameters, lambda d and lambda u, which are different. So it sort of weights. It'll weight the loss of like a desirable example versus an undesirable example differently, much like we have like different perceived value of like gains and losses. And then they also have the reference point here is the general like it's sort of the like expected value of like of seeing the distribution, I think, or something.
Like a most common one I see is like this monthly business review, where
I didn't quite understand like this part, to be honest.
I think it's the KL. So it's the, how do I put it? It's the distance between the reference model, which is probably like the initial model, and the current model in terms of like the example, the generated example. So you'd probably take like the entire batch, calculate the likelihood of each example with the reference model and the actual model, and then just calculate the KL divergence, assuming that those probabilities are like a good representation of the entire distribution.
So you want to keep, so does that mean basically you want to keep like the distributions of the reference model and the new model like roughly similar, while trying to improve the likelihood of like generating a desirable example or reducing the likelihood of an undesirable example?
I think that's baked into this loss function. But I also think that it weights it differently than you would in PPO based on looking at the formula. Like you use that reference value as a as like an anchor, like we saw around the origin in those plots. But I definitely think it's doing that.
Yeah.
Most people have like different sectors and that there are like governance documents that you kind of thing. Like,
yeah.
Basically,
yeah, which is kind of like what they're saying here.
For this little bit already out like 80%.
So this KL divergence is the like reference point.
And then the rest is just that last 20%.
Which I guess kind of makes the sense because they add some intuition here. So they say that KTO works because if the model increases the reward of a desirable example in a generic way, meaning what I take to mean like if the generation distribution fundamentally changes from the reference model, then like that penalty will be high, and so no, like it won't like improve the loss. Meaning like the way it has to learn is it has to learn to like very specifically generate like the desirable outputs without fundamentally changing the distribution over the batches of data that it sees.
So what I guess I have slide is not so much about that tolerance everything around like you said, like editing.
So yeah, they mentioned here how they calculate that KL term. So they take like the inputs in the data set but match them with like unrelated outputs and then calculate the using these like unrelated input output pairs. They compare the distributions of the new model and the reference model. So then we get to like the lambda D and lambda U. So again, this is like weighting how we learn from desirable and undesirable outputs. And they determine empirically, as I understand, that a good range of this formula is between 1 and 4/3. So the way they do that is they set one of the lambdas to equal 1, and then they vary the other one. But it's based on how balanced or imbalanced the data set is. So if there's an equal split of desirable and undesirable examples, then they'll have one of the lambdas is 1 and the other one is between 1 and 4/3. Whereas if it's very imbalanced, like 10% undesirable and 90% desirable, or the other way, then they change the ratios or the lambdas to accommodate that ratio. And yeah, as it mentioned, it's more gain sensitive than loss sensitive as opposed to humans. So empirically, they determine that placing a higher weight on the gains from desirable outputs leads to better performance than the other way around, which is kind of interesting because I would have assumed it's the other way around. But they do mention it's also task dependent, which makes sense because some tasks you might want to, you might benefit from heavily weighting the undesirable outcomes. So
Yeah.
getting back to your question from the beginning, sorry. So the way they get these desirable and undesirable examples in this experimental setup is they basically take the preference pairs that are used in DPO or RLHF, and they assume that the one that's preferred comes from a desirable outcome distribution, and the one that's not preferred comes from an undesirable, or is labeled undesirable. So kind of simply, they sort of split the data set, split the pairs into individual examples. But one thing they also do, because they recognize that then the data set becomes preference pairs, but just split. So one thing they test also is what happens if we only sample one of those outputs from a preference pair and do alignment with those. So the model never sees the pairs of preferences, it just sees one or the other. So you can assume that it's just like the examples are unrelated, and it's just seeing good or bad examples from different inputs. And interestingly, they show that it still works well, which is promising. So maybe I'll just go to the chart here to show the output. So what we see is that, well, we see a couple of things. So supervised fine-tuning plus direct preference optimization versus supervised fine-tuning KTO seems to match, the performances seem to match. So it's competitive with DPO. One of the really surprising outcomes of this is that the performance of just doing KTO alignment without supervised fine-tuning is almost as good and matches in some cases the performance of supervised fine-tuning plus KTO, which I found quite mind-boggling. The fact that you don't need to do instruction tuning and just using this alignment method, you get outputs that are as good as doing instruction fine-tuning and then alignment. So that's a pretty fascinating example, and they kind of dive into, yeah, Damien.
I was just wondering whether that's related to the idea that to some of these findings that large language model providers have found that people actually prefer certain types of outputs regardless of whether they're correct or not. So
yeah,
maybe it's the model doesn't necessarily need to be good at following instructions as long as it outputs in a way that's aligned with human preference.
Yeah, and they kind of go into one of those possible factors, which is the length of the output. So what they explore is after instruction fine-tuning, the length of the outputs tend to hover around I assume this is tokens, a few hundred, 100 tokens or so. But if you just do direct preference optimization without instruction tuning, you start getting really long output responses, which I assume are undesirable generally, even though they might be potentially correct. I guess whatever correct means in this case. But it seems with KTO, it manages to keep the length of the responses sort of more constrained. And that could be a factor, like you said, in the preference. I know for sure I get pissed off when ChatGPT, when I ask a simple question, ChatGPT gives me 3 paragraphs or something. I know I get pissed off. So maybe there's something there. So yeah, KTO matches performance of DPO, and also it matches it or close to matches it without supervised fine-tuning, which is interesting. One other interesting outcome is they they check what happens if, so now that we've split the preference pairs, one thing we can do is we can create an imbalanced data set. So we can just keep removing desirable examples and see how that impacts performance. So as you'd imagine, like as they remove desirable outputs, the performance drops. But however, like it still remains with the Llama 7B case, like competitive with DTO, even better, even when 90% of the desirable examples are removed. So effectively, it has much less data and less signals, but it manages to be competitive, which is fascinating. And really, it's fascinating and also really like exciting because, as it's mentioned, like preference examples are hard to gather, whereas like for example, having in a chat experience, having a thumbs up, thumbs down button is like easy for users to click, and so this allows you to align models based on thumbs up, thumbs down examples, and with an imbalanced data set, which probably is likely the case. Like most people might not give thumbs up when they get good outputs, but they might be pissed off and give thumbs down on bad outputs. And so you can learn with an imbalanced data set where you have mostly undesirable outputs, but some desirable. So that's exciting. And then they do another experiment, which I want to touch on, which is, remember I was saying how they do some experiments where they subsample only one of the outputs per preference pair. So effectively, the model only sees one input-output pair for each input. And they show that even with one y per x, it still beats DPO. It doesn't do as well as like having all of the data, but it's operating off like much less data, like half the data. So that's kind of interesting. Yes, Peter.
I actually had I have like a more of a conceptual, I don't know, thought about what you were just talking about, this idea that you can train off of only negative examples. Because I like wonder, or off of primarily negative examples. Because I think it's possible, but I also say to myself, if you don't have many examples of what's good, then I could see you learning not to do stuff, but not necessarily to do stuff, like as a language model. So I don't know if we'll ever be able to, I wonder if we'll ever be able to train a model off of like only negative examples.
Yeah, I mean, that's what this point is. And like, I wonder how much they handpicked this example of like Llama 7B, but effectively they are saying that even with no desirable examples, you still have a 30% win rate versus the target. So pretty strong. Yeah, Benny?
I was just wondering whether maybe the presence of negative examples is more like visible to the human rather than like it's harder to, I don't know, it's a weird conceptual take on this, but maybe like it's harder to spot positively expected examples, and maybe like negative examples are much more prominent and like immediately cause the person to disapprove of the example. So even though the model might not be learning to specifically output good things, as long as it doesn't output negative things, like undesirable things, the overall score might be higher.
Yeah. So yeah, but they they do also another experiment where they take Zephyr B, which is a instruction-tuned Mistral 7B model, and they show that substituting KTO for DPO in this case improves performance across all the data sets, all the test data sets, and even in the 1y per x, it can improve it in like all except the MMLU, which is interesting. And they kind of go into this in another part of the paper, I think in the conclusion. They suspect that it might work better because KTO can, well, because preference data can naturally be quite noisy. So if you think about like preferences, well, like everyone on this call, given 2 pairs, I don't think we would all perfectly align in terms of like what the preference is, which one is the preferred one. We might have different ideas. And so there's it's a naturally sort of noisy data set. And because of the way DPO and RLHF is set up, that can harm maybe the process of alignment, whereas KTO seems more robust to that kind of data. In terms of how it, like how the loss function is set up. So perhaps that kind of robustness to like noisy preference data means that it can perform better in these kind of different contexts or examples. So that's like sort of, I'm reading into this from like what they've said. So I'm keen to hear if you have another thought. This is kind of the what they say in the theorem in this section. So yeah, they mention like the preferences of 2 humans often contradict, which can, in the worst case, impact like the expected value of like of the generations of the preferences of like these both humans, whereas like KTO will not change like anything at all in terms of, it won't update itself if it sees these like contrasting examples. And that leads them to say, like, you know, it depends what context you're operating in, where KTO and DPO might work better in different contexts. And yeah, they even mentioned like even now, like with synthetic data generation from using other language models, that can also be noisy. Like we've seen biases in these models, like preferences. And so KTO can perhaps help in those contexts as well. And they mentioned the ultra feedback data, which is what Zephyr 7B was aligned with. So that could explain why there's an improvement across the board with using KTO. I mean, they kind of like, they have this like nuanced pitch of like which to use when, but I also just feel like, well, they do mention, yeah, if you have like just desirable, undesirable outputs, then you're better off using KTO. But if you have a preference data set already, then I guess the choice is more nuanced. But I'm unsure in what context. So what I love about like the binary format is like you can just see that being collected more easily in the wild, whereas preference, I think you have to like explicitly want to collect preference data. Can anyone think of like an example where preference data is like naturally occurring?
I think it actually occurs in a lot of places, but you have to make an assumption about it. Like when I listen to music, if I get suggested a song that I don't like, I'll usually skip it. Whereas if I like the song, I'll keep it. So you have to make the assumption, like if you wanted to collect preference data there, that action of skipping a song early shows dislike and listening to the song shows like. Whereas with like you said, YouTube Music and YouTube and all these other platforms, they literally have a like and dislike button. So
yeah. And the cool thing is like as they mentioned here, you can turn like different kinds of signals into like desirable and undesirable. So they mentioned like toxicity. Like if you have something that can detect toxicity, you can use that to label examples and then align a model based on those, rather than needing someone to like label them, which is really cool because you can collect these. You can imagine collecting these way more easily, and then aligning your model to reduce toxicity.
Yeah, I would say any kind of sort of ranking type application. So any situation where you're showing, for example, 2 alternatives to somebody, then that gives you a preference signal.
Yeah, that's a good example. Awesome. So in summary, what have we explored today? Well, we have a new alignment method on the block. I'm really curious, like, Peter, I'm curious where you found this actually, and like if you've been seeing more noise around this, like whether you think this is something that's going to take off in terms of new ways to align language models.
I found it through Damien actually, because he was looking for new ways of training language models, I think. I haven't seen it take off yet, but it's pretty recent. Like the paper date is a couple of weeks ago.
Yeah, it's quite recent.
Like DPO came out at NeurIPS. I mean, it was out beforehand, but DPO came out at NeurIPS in December, and right now the state-of-the-art language models that are open source are trained with DPO. So who knows, maybe in like a couple of months they'll be trained with KTO, and if they're not, maybe they'd also indicate something.
Yeah, exactly. That's what I'm curious about. Their experiments. They did some experiments on Mistral 7B, but most of the experiments was on Llama, not even Llama 2, because it didn't have a 30 billion parameter variety. So, yeah, I'm quite curious to see. Hopefully, like Hugging Face has an implementation of this like soon or something, or someone will come out with an implementation. And
Hugging Face does have an implementation of it. There's like a KTO trainer.
oh, cool.
Yeah.
Nice. That's already out.
Yeah. There's a DPO trainer too.
Yeah. Damien, do you know how good those models are compared with their DPO version?
They're in like the first 100, I think, of the leaderboard. So some of them outperform other DPO models, but I don't think there's been enough experimentation to actually say like we've trained it for long enough with the right number of data sets to make it outperform like DPO, for example.
Yeah, I suppose. I wonder what, like, if they're using the same data sets with this trick of separating the preferences. Like maybe we need a new.
I think we might need
new data set.
Yeah.
Yeah.
I've been wondering, like, I think that DPO was a really big step forward from the perspective that I even wonder, was there like an equivalent to DPO before RLHF? Like, do we not have preference training objectives. Like, why did we start using RL to train on preferences as the first thing we thought of when we, or that the people who were developing this, because I don't know if I would have thought of it, but when they were developing this, and then we came to the point like, oh, we can just use a supervised objective has a much clearer signal to the model. We don't have to have this like extra model that we train to reward model that we train. And now with this KTO thing coming out, I'm like, I wonder if we're going to find that like a super simple training objective is best. That's like just some supervised training objective. Yeah, I don't know. We'll see.
Yeah.
From the beginning, Vahan, like at least in the OpenAI papers about like for Instruct GPT where they introduce RLHF, they were doing it with preference data.
So I can't think of a good reason why reinforcement learning was used.
Well, the leap was so because they thought like, oh, we have preference data, let's train a reward model on that preference data, and then we can do RL on it. No, but then wasn't the DPO leap the fact that you actually don't need to train a reward model?
Yeah, that you can use a supervised objective, which is equivalent.
Yeah, just kind of. I guess maybe it wasn't immediately obvious.
Yeah,
Maybe
everything's obvious in hindsight, right? But not obvious at all when you're doing it.
The OpenAI team are fallible after all. They're mortal. Cool. I realize we're over time. Thanks everyone for diving in today.
Thanks for presenting, Gerard. This was great.
Very interesting.
Thanks, Gerard.
Bye-bye.
Very interesting. Thank you.
Thanks.